Hello, everyone. I'm Jorge López-Ordovás from Aston University, and I'm going to share my work done at Aston University as part of my PhD, methodology for the design of a rotary kiln for the pyrolysis of biomass. This work was done by me for my PhD and supervised by Katie Chong and Professor Bridgewater. And here we go. Well, we've got a lot to show today, so I will try to go quite fast. So we will start with a bit of background. I will explain a bit what's pyrolysis, although Frederick already did a great work explaining everything. I will show my objective, the slow pyrolysis reactor design, what are the characteristics, and then the main parts of it. So the bed of solids, heat transfer, the kinetics, how do we integrate everything together, and then how is the user interface and the conclusions. Everything will make sense along the presentation. I did all my work in the Energy and Bioproduct Research Institute in Birmingham, which is here on this fantastic picture. So firstly, I'm the Early Stage Researcher 3, based at Aston University, and I belong to the work package for pyrolysis routes for dry feedstocks. It's quite related to the work done by Chemislov, the ESR4, and I was collaborating quite a lot with Felipe, who was my colleague at Aston. And this is a fantastic picture of I think it was the last meeting we had at Edinburgh in October 2019, before all this started. So what's the background of my project? So basically, the world is facing many challenges: the depletion of the fossil fuels, climate change, the increase in energy demand, the waste. So, well, ideally, what we could do is transforming the waste we are producing into energy. So there are more people in the world, we are creating more waste. So the ideal thing would be to transform all the waste we are producing into energy. So for that reason, we selected pyrolysis as one of the most promising technologies coming. It's defined as the thermochemical decomposition of the feedstock in the absence of oxygen. And it's giving three products, mainly char, bio oil. I like calling it pyrolysis oil because bio oil is only related to fast pyrolysis and wood. But yeah, anyway, and then we have permanent gases. We are GreenCarbon, and we focus on the char product, on the solid product. So we mainly use slow pyrolysis, characterized by low heating rate, longer vapor and solid residence time inside the reactor, and lower reactor temperatures, between 350 and 600, roughly. All these parameters and values change across literature. So this is a typical scheme: the absence of oxygen. We produce the three products, and these two are together in the reactor. That will be a key for the work later. So in my work, during my project, I just started analyzing all the technologies for slow pyrolysis. There are many. We had the batch processes with the Argentinian kiln, Missouri kiln, etc. Then we had some semi-continuous processes which were fed in batches, so like the wagon retort or the twin retort. And then we had the other technologies which were totally continuous. They were fed and the product was discharged totally continuous, not by batches. So they were Lurgy, Reichert, and Lambiot that required large particle size. And then there were others like Herzog, moving agitated bed, rotary kiln, and auger reactor. Well, from the title of this presentation, you guess which one I prefer, right? So I selected the rotary kiln as the most promising technology for slow pyrolysis. I was looking on the literature, and then I found that there was not a specific methodology for the design of a rotary kiln. Here we have a picture of one of them in pyrolysis. And yeah, I decided to go to that way and try to not only create a methodology for the design of a kiln, which is well known in industry, but I also tried to create, this is a scheme. I also tried to create a small model that designs automatically a rotary kiln when the inputs are given. So this is the basic scheme of my project. I was given the model, the feedstock, the capacity, and the temperature of preferred product. And then the model was combining these three aspects I will go through along the presentation to give some of these outputs. Well, all of them: the height of the bed of solids, the diameter of the kiln, the length, the angle, the rotational speed, and also just like a bit all other aspects like ceilings, all the bearings of the reactor. Finally, the results we also obtain are the product distribution, the residence time, and also the temperature profile of each of the components inside. So the three aspects we are going to combine here are the bed of solids, the heat transfer, and the kinetics. They all work together to design the reactor and to make the reactor work. We need all of them separately. The solids are flowing along the reactor. We need the solids to achieve a certain temperature, and so we need all the heat transfer and we need all the heat flows. But of course, we're talking about pyrolysis. That's a chemical reaction, and we need the kinetics of the pyrolysis for that. All of them should be studied and combined for the design of any reactor, and it gains special importance on the rotary kiln, on a slow pyrolysis. So for the bed of solids, one of the first parameters I came across during my research was the Froude number, which correlates the centrifugal, the inertial, and the gravitational forces. So it's represented by this formula. This is the rotational speed to the power of 2 multiplied by the radius and divided by the gravity. But what does it mean? It doesn't seem to mean like a lot. Yeah, it means a lot when we came to Mellman classification, which classified the different motions of the solid depending on the Froude number, as we see on this table. So we have all these 6 rolling motions of the bed of solids: slipping, slumping, rolling, cascading, cataracting, and centrifuging. Each of which has different characteristics, has different features, and they are very. We could be discussing a lot about which one is better or what is more appropriate for this. But we see here, for example, to go to the extremes. In this case, centrifuging is just that the solids is like adhered to the wall, and it keeps rotating with it due to the high speed of the rotational speed of the reactor, of course. So it doesn't mix, it doesn't do anything, and on the other hand, you keep heating the part in contact with the wall, but then the part inside doesn't heat up as much as the other one. So we have a lot of temperature gradients. On the other hand, we have slipping, in which the wall moves, but then the solids don't move at all. Like they always remain on the same position, on the same coordinates. So yeah, we can study a lot, but from all of them, rolling motion was selected as the most promising option because it included some mixing characteristics, but without any kind of slumping. So it was not adhered to the wall and then falling over the bed of solids, which would create, I agree, a more turbulent flow, but at the same time, it may crush the solids, or it may have some effect with that. So then the bed of solids had to give us the contact areas between the wall and the bed of solids and the gases inside the reactor, and the gases inside the reactor and the wall. We came across with this interesting graph. I developed it mathematically. The F represents the filling degree. So it's the portion of the surface that is covered by the solid. So the area of contact divided by the radius and the length of the reactor, of the bed of solids, follow this strength. It's just a simply mathematical development from the basic formulas of areas, but it's quite representative because with the filling degree, we can know the contact area. So it adjusted to these equations quite well. We now come to the heat transfer. So we are talking about a very complex system. We have a very hot wall heated up by some combustion gases, and we have a bed of solids, we need to increase the temperature. So we have the three heat transfer methods. We have the conduction, which occurs when two materials are in contact at different temperature, and we calculate it through this equation. We have convection, similar to conduction, but one of the materials is in movement, and whose heat flow is calculated through this equation. In this case, the most difficult part is going to be calculate the convective heat transfer coefficient. And finally, we have radiation, on which materials irradiate energy due to absolute energy higher than zero. And we need this complex formula. Just to clarify, the F12 is the view factor and represents the amount of energy that leaves the surface 1 and hits the surface 2. That was one of the main challenges in this research as well. So I don't want to. I will explain a bit later, but I don't want to stop by a lot on these aspects. Everything is on my thesis, which will be public shortly anyway. So for the kinetics, I decided to use the isoconversional methods instead of the isothermal methods because we needed to study the widest range of temperatures available. So we use these four methods: Kissinger, KAS, FWO, and Friedman. Just to say, the Kissinger, KAS, and FWO are integral methods, and Friedman, it's a derivative method. It goes with the background noise it can have during the experiment. All of this was done on TGA, thermogravimetric analysis, and we studied all the peaks and everything to come to the following conclusions. So we found out the pre-exponential factor and the activation energy we needed to simulate and to model the behavior of the solid during pyrolysis. We used these heating rates: 1 Kelvin per minute, 2.5 Kelvin per minute, and 5 Kelvin per minute. So the continuous lines are the values of the conversion with the values we obtain, whereas the discontinuous lines are the real values of the model. Are the real values, not from the model, from the actual experiment. So we saw it was not very accurate because it doesn't match very good. So instead of just varying the reaction order, we tried to analyze it analytically. So we created a parameter called error or total error, which quantified the variation between the conversion of the model and the experiments during all the experiment, each individual experiment, and during all heating rates. So when we optimize the reaction order for wheat straw, we had, well, I will show you now the feedstocks. We see that it matches way better than before, and it's the optimum because the value of the error was minimized. That's why we had here the absolute. Sorry, Christian, are you gonna say something?
You have 2 minutes left.
All right, perfect, thank you. So the value was minimized. And finally, for the refuse-derived fuel, wheat straw, and wood chips, we obtained these values. We had also the product distribution to calculate. The charge yield was calculated for the TGA experiments. The pyrolysis vapors were estimated from some experiments my colleague Felipe Rego did. He will present also one of these days in the GreenCarbon conference, and was adjusted to these values. But now we had to simulate we had to integrate all parts together. So what we did was dividing the reactor into slices and calculating each slice individually. So on each slice, we gave some temperatures, moisture content, conversion. Each slice had this algorithm for the heat transfer, and then gave the outputs. Initially, I put 25 steps, but had to increase to 100 to convert properly. Sorry, I haven't got time to explain this diagram, but it's quite interesting. I will be more than happy to explain later. For the user interface, we use this user interface when we indicate feedstock capacity, the type of feedstock, the temperature we want, the carrier gas if we want, if we don't, the feedstock shape, and the moisture content. And then we are given all of this information, which is really useful and it's what we need. Among other, we have the mechanical specifications here.
Jorge,
and then the conclusions of this study is
that,
So the conclusions are that the three essential aspects in the design of a pyrolysis reactor are the kinetics, the behavior of the bed of solids, and the heat transfer. So the solution of each aspect should be solved individually but integrated together. The reactor was divided into slices. There are several assumptions to develop this model, but of course these assumptions can be developed further and improved. So thank you very much for your attention. Sorry I ran a bit over time. So if you want to contact me, I have these two emails. This is my university email. It's going to be active until the end of this month. Alternatively, you can contact me here in this email. And this is the Twitter for further news and updates on this project. Thank you very much.
Okay, thank you, Jorge. We have no time for questions. So if you have any, you can contact Jorge personally.